Hello, welcome to this video. In this one we're going to go over the x86 and x64 assembly, just some sort of basics that you'll need to understand for reverse engineering and low level computing. And this is by no means a be all and end all. In this video we're primarily just going to be going over the main registers that exist within this instruction set and what registers are, sort of how computers function at a low level. We're not going to be going too in depth, but as a reverse engineer or someone who's getting into low level stuff like hacking, things like that, or some sort of exploit development, this will definitely help you. And this also primarily does affect Windows systems. Obviously different instruction sets generally are going to not necessarily dictate an operating system. Well, they can do things like ARM, things like that, where it's going to potentially be on Linux, but it's out of scope for this video. We're not going too specific, but generally when I'm talking about certain things that impact certain registers, things like that, we're going off the Microsoft Windows sort of way of doing things, like different calling conventions, as you're going to find out, things like that. I'm also doing a separate video for things like calling conventions and certain parts of this video that I'm going to talk about as well. So if you're hearing this now, you're thinking, what does this even mean? Then that's great. You're not this topic is new. This stuff is new to you, so that's obviously why I'm doing it. But without further ado. So some prerequisites, as I just explained, they should be used as an aid as to a developed understanding already. If this is your first sort of exposure to this content, or if you're very new to reverse engineering, I highly recommend you watch other videos as well in conjunction with this, and actually go and sort of try it out for yourself. If you've got access to a computer, if you've got any sort of computing device, there's no reason why you can't do it. Go and have a look to see how things work. I'll put some things in the description, things that really help me, and some very knowledgeable people, for instance, OA Labs and Hercore, people like that, people who are far more knowledgeable than I'll ever be. But they're the people I look up to, and some mentors of mine. So I'd highly recommend you go check them out. In general, just low-level basic knowledge, obviously knowing how a computer works is definitely going to help with this sort of thing. If you're jumping into this and you've never even touched code before, I'm not going to say it's impossible. Things like that, it's just, it can be very difficult. Sometimes having no knowledge of anything and going straight into it is good, but I'd say for a lot of people, especially if you are a programmer, let's say you're a web dev and you're going straight into this, it might be a bit more difficult. But having an understanding of low level things or just programming computers in general is probably definitely going to benefit you in this case. So right away we're going into memory structure. So obviously computer memory, your RAM, your random access memory. This is how things work. Any sort of computing device that you're watching this on now, television, phone, computer, whatever it is, it's going to use some form of random access memory, and it uses certain structures. So for instance, a bit is a structure which contains 0 or 1, so it'll be a Boolean value, and then a byte is a collection of bits, and a byte is 8 bits, and it's also starting from 0, not 1, and that is something known as index based. And in computing you're going to find that a lot. So things like arrays, things like that, they always start at 0 and not 1. And in this case, a collection of bits being a byte, it goes from 0 to 7. And how we're going to think of memory, I'm going to break it down so it's a little bit easy to visualize. I'm going to show you in a minute. Think of it as rows and columns. So left to right your bits, and then up and down will be your bytes. As I'm going to show you in a second, it might sound a bit confusing, but we'll take your slow time. Inside bytes, they contain the most significant bit and the least significant bit, and this just refers to the respective highest and lowest point in memory. Again, I'm going to show you this in a second, so it's a little bit easy to visualize. And typically memory is represented as going from right to left, and this is just a convention, but it does come into play in a concept known as Endianness, which I'm going to talk about now. And in general, with a lot of things in computing that you're going to find out in this video especially, a lot of these things are just concepts, and generally I'd like to try and stick to it. For instance, depicting memory from going right to left. The reason being, if you start changing these things around, things can get confusing, especially when you start looking at things like the stack and seeing how that's laid out. If you start changing how people, or in general, how it's been laid out for years, and then you start doing it your own way, if it helps you understand it, that's great. But obviously when you try and change it, then you get confused. That's when you run into issues. So this is structure of memory, a more visual example. So as you can see, going from right to left, right being our least significant bit, and then the leftmost being our most significant bit. So going from 0 to 7, these are all bits. So 0, 1, 2, 3, 4, 5, 6, 7 bits, which then will make up 1 byte. And as you can see down here, these 1 bytes will then form together to make other various structures. In this case, this is a double word, so a word being 2 bytes, and then obviously we have 4 being a double word, And this is coming into your programming, things like that, where all these sort of things come into play. And if you've ever, I don't know, touched a level language before and you think, oh, what is a D word, a double word, or when you get a Q word, things like that, quad word, all those sort of things, this is where they come from. As you can see here as well, think of it as a table, rows and columns. Each row represents a byte, and each column represents the bits, that kind of thing. As you can see as well, in x86 and x64, so x86 is 4 bytes. It's sort of the maximum that they will work off. It's 32-bit, being 4 bytes, so 8, 16, 24, and 32. And then we have x64 being 64 bits. As you can see, it goes all the way from 0 to 64 bits, each one of these being 8 bytes, so there's 8 in total. 1, 2, 3, 4, 5, 6, 7, 8. But as we know, it's index based, so it will go from 0, 1, 2, 3, 4, 5, 6, 7. I won't get too hung up on that if that's boggling your mind. A little bit index based, it's not so much to do with memory, that's just computing in general. But this is the sort of structure, how memory is sort of laid out. If you needed more of a visual example within RAM, this is sort of, I like to think how it's going to look, and it might help you out. So now we'll talk about endianness, and this just refers to how bytes are arranged within memory. So you have 2 types of this. You have big and little endian. So big endian, it stores the most significant byte in the lowest memory address, and little endian, it stores the least significant byte in the lowest memory address. It's basically the opposite of each other, as I'm going to show you now. And these both exist due to different types of data storage and access, such as English being read from left to right. So as I just said there, English is read from left to right. Other languages such as Arabic, things like that, they are read from right to left, and as well other things as well that come into play. But this is why this is most useful here. Obviously, it's going to be stored differently in memory. So as you can see, big endian, our most significant bit is stored at our lowest memory address. So in this number here, our most significant bit would be this portion at the front, the 0x12, and this would be sort of where our 7th bit is sitting here. So most significant bit sits right at the front, 0x0, and then we go 1 byte in, 3, 4, 5, 6, and then finally 7, 8 at the end of the number. The least significant bit is stored there. So if we go back here to a little example, the least significant bit and the most significant bit, as you can see, big endian stores the most significant byte in the lowest memory address, things like that. Sorry as well, I feel like I should mention this. Big and little endian, this refers to the order of the bytes, not the order of the bits. So when I'm saying that, I might have accidentally confused, I've said it wrong. When I'm saying bit, I'm talking about bytes. So as you can see here, this first byte is stored in the lowest memory address. It's big endian. Yeah, not bit. Sorry about that. Find the little endian. The lowest memory address stores the least significant bit. So as you can see, the least significant bit in this the least significant byte in this example, being 0x78, is stored first, and then we will have 5, 6, 5, 6, 4, 5. 3, 4. I read that wrong. 3, 4 there, and then finally 1, 2 there. So just sort of different systems for different types of data store, essentially. As I've already explained, the reason for that is just the need to store data differently depending on your circumstances and programming language and architecture, things like that, or in some cases the type of language you'll be using. Big endian format is more popular among networking protocols due to age. So these protocols were developed obviously a long time ago, and people sort of said at the time that we want to use big endian, and it's just sort of not changed since then. Most modern PC systems are either going to be bi-endian, or as in they're going to use both, or they're going to use little endian. Most of them will use little endian, and that's arguably due to efficiency, for a number of reasons. It's a good if you're more interested in this sort of thing. I'm not going to go into it in this video because again, I don't make computers and I'm not that knowledgeable on this topic, but it's definitely a good read if you want to have a look. So what the efficiency sort of thing means is it's going to take less instructions to access certain or it's going to be faster to access certain things in a certain format, essentially, as in the argument of little endian versus big endian. And there's arguments on both. There's sort of like a 50-50, as in why one's better than the other, and there's not really a better answer, but yeah, there's not, as it says there's not a definitive answer as to why, but again, highly recommend you read up on it. And unless you work at low level and hardware level, is not going to matter to most people. Again, for most developers, it's probably not going to impact your day-to-day, as I've said, unless you are sort of a systems engineer, things like that. And finally, registers. Registers are part of a process design. So a register is a hardware piece of the processor which you're going to use to interact with the software. This is a built-in part of it that makes accessing things infinitely faster. The best way, if you're struggling to understand this, I would like to mention, if you are familiar with computers, you think of cache in a processor that exists there due to it's sort of the hardware component, the small bit of memory that exists for very, very high transfer speeds, and it's very fast and efficient. This is the same sort of thing, just at a much lower level. These exist because it has to be so fast and just instantly available. This is why the registers exist. So by using static locations instead of memory, it makes accessing and writing memory much faster. Similar to how caching works, as I just explained. A hardware implementation for a software solution. So registers are built into a physical component, as in the processor or some type of CPU within a system. And these registers may have a specific purpose. Some do not, as we're going to touch on now. And registers can be volatile or non-volatile. This just means that they across function calls, when you sort of say hello world, things like that, some of these registers values are by default going to change. Some of them aren't. So if they're volatile, they can change. They might necessarily won't, but in other cases they might. That's just sort of the volatility of them. And the ones that aren't volatile, and no matter what, aren't going to change across function calls. And as it says there, this will become a lot clearer later on. But I was just having a drink. So as we already know, x86 registers are 32 bits in size and begin with an E. This E just stands for extended, and the x64 equivalent of these registers will begin with an R, and that R just stands for register. So for instance there, the RIP versus the EIP register. So what these registers stand for: the instruction pointer, the register instruction pointer versus the extended instruction pointer. One of those is 64-bit, one of those is 32-bit. x64 registers are 64 bits in size, and the R in the naming scheme, it just denotes register. From what I can read up on this just refers to sort of a convention that people were discussing back in the day when these things were invented, or many yonders ago. Registers by that point were just only 32-bit, and 64-bit was quite a new thing. And they were sort of saying to add this sort of new set of registers, which as you'll see in x64, it's got all that new space, so they want to create and sort of use as much of it as they can. And the naming scheme was going to call them like R10, R11, things like that. And the 64-bit registers then needed to be addressed. They'd probably just be addressed as the instruction pointer or accumulator register. Whereas then instead someone suggested that, why don't we just go off the same naming scheme? So instead of calling a set of them like R and then a number denoting the register, we'll just call all the 64-bit registers with an R. So the accumulator register then becomes RAX, that kind of thing. So general registers, these are the most used registers that exist, and there's a select few of them. They exist for a specific purpose and are used during most application life cycles. So every time you load an application into memory, when you double click it or when your computer starts up, that's sort of its thing beneath the hood, it's loading things into memory and it's running them like that. Just because you're not doing it, that's just sort of how it works. This is how they're going to be used, it's how this works. So x86 contains 8 general purpose registers, and x64 extended this to 16. Obviously you've got double the capacity, so therefore you have double the space to do things and play with them, and you've got all those new bits on those existing registers as well. So general registers, the different types of registers you can get, and again these extend across both x64 and x86. So starting off, we have the AX, the accumulator register, and this stores the results of arithmetic operations, and this register will also be used as a return value for your function. So for instance, EAX is the x86 equivalent of that, and RAX is your x64 equivalent of that. Your base register, and this is commonly used to store common values in functions to speed up the process. So for instance, when your function declares something, or when it's performed an arithmetic operation, this is where it could end up in the base register. The counter register uses a loop counter and as a function parameter and calling conventions. Just before we carry on as well, I'd just like to mention these are not the be all and end all. This is not only what they're used for, just a short example just to give you sort of an idea of what these things can be used for. Finally, the stack pointer register, and it points to the top of the stack, the last item which was pushed onto the stack. and then we have the BP, the base pointer register, which points to the bottom of the stack where the stack is sort of created. The DI, destination index register, and this is used as a point to destination. So for instance, when you're accessing an array, things like that. And then your source index register is used as a pointer to the source of data. So you use this in sort of like a data stream. So your source index will be used to the pointer of the data, the array, and then your destination index will be used to where you want to go inside that array, that kind of thing, within arithmetic operations. And then finally, DX, your data register, and it's used for short-term storage and function call parameters as well. This will all become a lot clearer later on. For instance, your calling conventions, what some of these registers will be used for, or things like that. Finally, accessing registers. So accessing registers can be done in multiple ways depending on the register. The full register will be 64 bits. Half the register will be 32 bits. This assumes we're on a 64-bit computer. Obviously, if we're on 32 bits or x86, it's going to be different. We're not going to have the extra 32 bits on top of that, so we're going to only be able to access the 32 bits, the 16-bit portion, and then potentially the 8-bit portion, depending on what register we're using. And finally, the lower 16 bits of the register can be split into two 8 portions of higher and lower memory. This key bit only exists on a select few registers, which I believe is specified on the next slide. If I haven't, I'll have to go change that quick, but I believe I have done. So a register diagram here, this is what I was meaning by that there. So obviously, as you can see, on a 64-bit register, we've fully doubled our capacity. So in a 64-bit register, we have an extra 32 bits here. In a 32-bit register, we just have split into 2 portions. So, or generally split into 2 portions, we have 16 bits, and then a further 2 8 bits here, which can be split down into 2 8-bit portions here into higher and lower memory. So all registers can be accessed in 16 and 32-bit mode. So that basically just means we can access any register that exists as a 32-bit value or a 16-bit value here, but only the accumulator, counter, data, and the I've actually forgotten the name of the register. The base register can be accessed in 8-bit half. So only these registers specified here can be accessed in this 8-bit portion here. So the upper and the lower memory of the 16-bit portion of memory. Only these registers here. Here's a little chart. If you want to pause the video and take note of these down. So as you can see, our 64-bit registers here, our 32-bit equivalents, our 16-bit equivalents here, and then finally our 8 bits. So we have the accumulator higher, accumulator lower, base pointer higher, base pointer lower, counter higher, counter lower, and then we just have stack pointer lower. So this base, any of these registers here will just be accessed as the 16 bits, and you'll have to just sort of go through that way. Whereas in this one, you can access the higher portions and lower portions. Whereas in these lower portions here, you're just going to be accessing the full 16 bits. Finally, general registers on x86. We have the EAX, which is the accumulator, EBX, the base pointer, ECX, the counter register, ESP, the stack pointer, EBP, the base pointer, EDI, the destination index, ESI, the source index, and EDX, the data register. The same as x64, just obviously we have less of them. Well, we have the same general registers on each because that's how they work. We have more on x64 because we have more space, but they're just the same with a different name, and obviously less space. Finally, our general registers on x64. As I said, our main registers stay the same. We just add a whole new bunch of registers for whole new different reasons. For instance, we have extra registers. Why not use some of them as a function call, things like that? And these are, with all this extra space, we may as well utilize it basically. In this video, we're not going to be discussing the purpose of these extended registers. Potentially I could do that in another video, but generally they're not too well. They are important, obviously, but just for most people, probably, yeah, not too important. We're also not going to be discussing floating points, but again, art scope for this video, but potentially cover in the future. So starting off, the RX register, the accumulator register, it's used as the return value of functions, so in EAX and RX respectively, and it's technically volatile as the value will change depending on the function's return value. So this will change across function calls. Even if the function doesn't have a return value, under the hood it does. It will just return a 0 or an empty value, things like that if it's a void. The register is used in calculations such as multiplication and division, and certain instructions will specifically use this register for division calculations, things like that, or division instructions I should say. Finally, it is a nice little diagram of our register here. So our x, the full 64 bits, our lower 32 bits being EAX, and then we have the lower 16 bits which you can access, and you can access the 16 bits in 8-bit halves in higher and lower portions respectively. And this is a theme that's going to sort of go across this video. All the registers are going to pretty much look the same, not going to differ. So RBX, the base register, the base pointer register, often used to hold the starting location of arrays, is often set to common values used throughout functions for efficiency. There's no specific use for it, and it is non-volatile, so across function calls this is not going to change. RBX register here, very similar to our register. Obviously we can access lower and higher portions of memory here as well. Finally, the counter register, it is volatile, so it will change across function calls, and it is used as a counter during loops and also certain instructions as well. It can be used as a function parameter during fast call, and the first two parameters will be stored in RCX and RDX, so in that calling convention there. First parameter will, provided it's not a floating point, will be stored in RCX, and the second will be in RDX respectively, if using the fast call calling convention. In class member functions, pass pointer to base class object is placed into RCX no matter the calling convention. So when an object is calling a function, things like that, the base class pointer will always be stored into RCX, just across different calling conventions, irrespective of them. R6 register again, same again, can access the lower 8 bits, the 16-bit there, nothing too different. The RSP register, the stack pointer register, it holds the address to the top of the stack, and when data is added to the stack, the value of RSP will decrease, and when data is removed from the stack, the value of RSP will increase. Obviously the stack grows lower. This will become more clear in another video that we do on the stack, but it's a bit out of scope for this video. If we were going to talk about the stack in here, it'd be very long, but the stack does deserve its own video. RSP register, as you can see, first different sort of register. We can only access the lower portion of the stack pointer, so we can't access the higher 8 bits, we can only access the lower. The RBP, the base pointer register, it holds address at the base of the stack, it's non-volatile, and it points to the current stack frame location. And compilers can use EBP as a data store if optimizations are enabled. So what that means is various compilers, they all have it, optimizations, where basically the compiler is going to say, look, to speed up certain things and to make things work better, it's a bit more advanced, we're going to do certain things, and one of those is using EBP as a data store. Obviously the good thing about that is it's more efficient, but bad things, it can be a little bit different and deviate from the norm for reverse engineers if you're not aware of it, and other things like that. That's the base point register. Generally, you're not going to find these registers changing too much. They're always sort of going to be used for the stack, but it's just something to be aware of. As you can see, same again, we can only access, as in the full 16-bit register, all the lower portions of it. If not, we won't be able to access the top half. We'll have to go from the BP register. The DI, the destination index register, is non-volatile and it's commonly used in string manipulation instructions such as the rep class of instructions. So this is sort of, as I was saying before, if you're using sort of a stream or an array, it's going to point to where you're going to want to go within that sort of operation or that array. Same again, you can only access lower portions of memory here, and obviously all remain the same. The source index register, it's non-volatile and it's used in stream operations to specify the source location, whereas RDI will be the destination address. So the source location is the starting point, and the RDI will be the destination address, or what sort of where you want to go in that data stream. So accessing, you'll see it typically multiplied index within an array. But look more of this when we go into reverse engineering, but this is just sort of how they're used. Nothing more to report. The data store register RDX is volatile, so it will change across function calls, and it is used to store data inside function calls. It is the second function parameter based on the x64 Windows calling convention. So it is used when you call functions. Your second parameter will be put into RDX. Finally, I'm going to talk about some special registers: the RIP and the EIP register, and the flags register. So the RIP or EIP register stands for the instruction pointer register and the extended instruction pointer register. As we know, it's just the x64 and x86 equivalent of each other. One of them is 64 bits, one of them 32 bits. But the instruction pointer register is unique, is that it points to the next instruction to be executed by the processor. So whenever you step through an application, if you have a look at it under the hood, this is going to always have a pointer to the next sort of portion of memory, and this directs the program flow of execution. It's the pointer to the next instruction to be executed. So the part of memory that or part of the program you're going to be executing now, if you go into a debugger, it's going to be different from the instruction pointer, because that instruction pointer is always going to the next set instructions to be executed. Good thing about the register is it will be typically commonly used in sort of attacks and as buffer overflow. So basically what you're trying to do is you're trying to target this register. You'll overflow the buffer that you are in so much so that it overwrites to this register, and it will form, if done correctly, a new memory address that's accessible within that region of memory, and it'll give you code execution. It's not something we're going to talk about, touch on, but potentially something I might do a video on if people are interested for it. Finally, the flags register. So flags in level of computing, it is just a register. It's a 32-bit register, and it stores the bits as boolean values, basically. So every bit inside the register has some meaning. So for instance, my mind has just gone blank. Carry register, carry flag, zero flag, things like that. I've not got a diagram for all the different flags, because again, the flags register could probably have its own video, but it's it basically is just it's the result of operations, essentially. So when something's occurred, something will change in the flags register, denoting that something's happened. For instance, the sign flag, denoting if the result of the last operation is negative. That is it for this video. There's nothing more I'm going to touch on here, but if you did enjoy, please do like and subscribe. Stay tuned for more. Please do support. It really does help the algorithm get some attention to these videos. These ones are especially the game hacker videos, are getting quite popular, and if you actually want to learn and gain something from these videos, this is the sort of knowledge that you're going to need to have as you're watching these videos. Just sort of tick through and think, oh, that's why that's done, and the more you start understanding it, the better you will become. Anyway, thank you very much for watching, and I hope you enjoyed.